All right, thank you. Thank you for the introduction. Is that good now? Okay. So what I'm going to try to share with you today is basically work by Coogan Thompson, who's up there. He just graduated, so Dr. Thompson. In my group at Virginia Tech, I'm in chemical engineering, and the work is with a bunch of different people. Liping Blue, who's probably in the audience, is a grad student Hong Chen, and he does all the DFT calculations. All right, so we're taking a step back and going to heterogeneous catalysis, and what I'm going to try to show you today is how we try to look at them as in a cycle like a homogeneous catalyst. So going to single atom catalyst, supported single metal atom catalyst, is the first thing is you want to use all the metals, every single atom. So that's the first thing. But as you go all the way to that limit, these single metal atoms have ligands. So they're not just free. The ligand can be non-reactive ligand, it can be a reactant, it can be a product, but it does change along the reaction cycle. This is a very nice example from the late Maria Stephanopoulos' group, where they showed that by modifying this ligand environment around the rhodium by using titania, they can get basically very high selectivity to methanol from methane for partial oxidation. So they have different and tunable properties as you can change the ligands. But then it helps us bridge homogeneous and heterogeneous catalysis, and hopefully I'll be able to show you today that we can do that. So this is iridium CO2 ACAC, and this is now iridium CO2 on a magnesium aluminate oxide. All right, so this is early work in my group. Several years ago, we started this work, and this is iridium on magnesium aluminate. So for CO oxidation, on a flat surface, on nanoparticles, we've learned that if you absorb CO strongly, then this is not a very good CO oxidation catalyst. That's how the catalysts get poisoned. So on single atoms, what we find is that it binds even more strongly than on nanoparticles. But what we've shown is that doesn't really stop the catalyst from turning over, and it's actually more active than on nanoparticles. So where is this higher activity coming from? Because we start shifting to a totally different mechanism when we start going at the single atom limit. What happens is, if you look at the reaction order of CO, basically you're changing the partial pressure of CO and looking at the rate of the reaction. For the nanoparticles, it's -1. This is what you would expect. It's poisoned by CO. But for the single atoms, it's positive order in CO. So it suggests a different mechanism. And we looked at that with spectroscopy and with DFT, and I'm just going to show you the DFT part. So again, on the nanoparticles, you're covered by CO, and basically you're limited by O2 activation on a CO-covered surface. So you get a positive order in oxygen and negative order in CO. You go into single atoms, and this is a low small, so I'm going to blow up this part, and over here, this CO acts as a ligand to actually activate this oxygen at the interface between the iridium and the aluminum. And the second CO comes and reacts with the CO at the interface. And that's what makes the catalyst more active. It's an Eli-Riedel type reaction, where now you're positive order in CO and zero order in oxygen. And we showed that through a series of publications in the last few years. Okay, so we can have a cycle through calculations with DFT. We can show that we can identify the resting state of this catalyst through spectroscopy and kinetic measurements. Can we do more? So this was on iridium on magnesium aluminate. So the question was, as we go from, for example, iridium on magnesium aluminate to iridium on titanium, does the rate determining step change? And can we identify more than one intermediate and the ligand environment similar to what Paul very nicely showed in his talk? So that was the goal when we started this. So first, I'm going to tell you how we synthesize the catalyst. It's wet impregnation, nothing very special. And we use iridium chloride on titanium, anatase titanium at pH 3. And then if we look at the vibration corrected TM, after all states, calcination when we remove the ligands, reduction, and after CO oxidation reaction, all we see is these single atoms. So the bright atoms here are basically the Z contrast image. These are the iridium atoms, and the rest is the titanium. And we don't see any clusters. So we're pretty confident that we make only isolated atoms. Okay, so we reduce the catalyst, and we absorb CO, or you can reduce it directly in CO. You get the same dicarbonyl of iridium. How do we know it's dicarbonyl and it's not two monocarbonyls? We do carbon-13, carbon-12, you flow both, and you, instead of getting 4 peaks for the 2CO12 and the 2CO carbon-13, you get actually 6 bands that are 2 COs that are 12, 1 12, 1 13, and 2 13s. So this is what we start with. You can call this the 3 cows, as Paul was showing earlier. And then you start flowing CO and oxygen, and you actually go to a monocarbonyl state. So you go from a dicarbonyl to a monocarbonyl under reaction conditions. And that's through, obviously, infrared spectroscopy. We do that through drifts. Okay, so if we flush away the CO and oxygen from the reaction, we actually end up still with this monocarbonyl, and it just shows you 15 inverse centimeters is the full width half max of that peak, which shows that it's pretty uniform. If you do this on magnesium aluminate, which is not as crystalline as the titanium, you get a much broader peak on the order of 30 full width half max. So what can we tell more about these states? So we go to synchrotron and we do X-ray absorption spectroscopy with in situ and in operando conditions. So we measure that after reduction, during reaction, and we keep going from between CO and oxygen to look at the different states. So this is the Fourier transform, and I'm not going to try to explain to you what these are in this short talk. I'll show you the fits in a minute. But if you look at these two, the dicarbonyl going to the monocarbonyl, you see a shift going to a higher wave number. That typically suggests that you're getting slight oxidation of the ingredient. And that's exactly what is shown here in the Zanes. You see a higher white line intensity as you go to under reaction conditions compared to in CO. And if we fit that, now we can go into, instead of just saying it's a dicarbonyl to a monocarbonyl, we can actually tell what's coordinated to the iridium. So in the reduced state, from the X-SAS fits, we also get about 2 COs per iridium, 2 oxygens from the support, and 1 titanium, and these are the bond distances. Once you go to reaction conditions, you get about 1 CO, now 3 oxygens, and the titanium. So not only we can tell what are the ligands that are basically the carbon monoxide through infrared spectroscopy, now with X-ray absorption spectroscopy, we can tell the whole ligand environment around the iridium. Okay, so this is basically what we call the resting state of the catalyst. Now we know that it's 1 CO through infrared spectroscopy, and then we know the rest of the ligands through X-ray absorption spectroscopy. So the question is, does this CO, is that a reactive CO that reacts with this interstitial oxygen? And the answer is no. If you go to just an oxygen or an helium at 170, you don't see any reaction, you don't see any decay of that peak. You have to go to much higher temperature to be able to start seeing this reaction happening. So what this suggests is that you have a second CO that has to come and react with that interstitial oxygen to basically go through, and that's a rate limiting step. And if that's the case, you should expect to see a positive order of 1 if you measure the reaction kinetics. So we go and measure the reaction kinetics, and we get a positive order in CO, close to 0 order in oxygen, slightly negative. But the order in CO is not really 1, it's half. So where's this half coming from? If it was what we are showing here, kind of an Elie-Radiel type step, then you would expect an order of 1. So we're getting half. So this shows maybe there is a possibility of a second rate determining step. So to look into it further, if there is a second rate determining step, and I'm omitting a lot of the intermediate steps in this cartoon here, all I'm showing is that there could be 2 rate determining steps. One of them is the CO addition and reaction to create this vacancy, and then a second actually has an oxygen activation step that doesn't have a CO dependence. So if we do that, then what happens, and this is not really shown here at all, if you go to a high partial pressure of CO, then you're speeding up this step, and this step is going to become rate determinant. And you should see a difference in the apparent activation energy. And that's what we see. That's why we basically say that the rate determining step, this one has a higher area. So this is as we increase the partial pressure of CO, we see a higher activation energy. The second thing is, if we go now to high temperature, then this step should be favored, and you would be limited by the CO addition on this step. And that's exactly what we see. At higher temperature, we see a higher order in CO. So everything is self-consistent with this very simple picture, excuse me, But this is as far as we can tell experimentally, because we have no access to any other elementary steps that are rate determining that we can isolate any of those complexes. So then we went to DFT calculations, and this is work by Lipping and Hongyang's group. And the first thing I want to point here is, this is the iridium C003 that we started with in the experiment. And they calculated, before we went to that one binding site, they calculated different binding sites on different facets, as well as on the same facet, which is the 101 anatase. And what I'm showing you here is the one that shows the closest agreement between experiment and theory. So the first thing is, this CO reaction with this interfacial oxygen has 1.6 EV barrier, compared to continuing here along absorbing CO and reacting to make this vacancy of 0.9 EV. So this is consistent with the experiment that we don't see this reaction happening, at least at the reaction temperature, and we get a positive order in CO. So then they calculated all the possible reaction pathways. There is branched here, other possibilities at each one of those. I'm not showing you here, I'm just showing you the lowest energy cycle. So I'm not going to go through all of these steps. What I'm going to point out is these two steps. This oxygen adsorption limited CO adsorption here and reaction to go from 1 to 3, and it has a 0.9 EV, and this oxygen dissociation and desorption, which is step 7, that has close to also 0.9 EV barrier. So we have two steps here, and if we just simplify this and derive the rate equation based on these two rate limiting steps, that's what we get. And this rate equation would simplify to just K7 at high partial pressure of CO, or at low partial pressure of CO, it would go to K1. And if you're in the regime that basically you have both, you're going to get a partial order between 0 and 1. All right, so this is consistent with the experiment as well, that if we increase temperature, we should go from one regime to the other. And that's basically what happens. You go from low CO order to the high CO order, and then the same thing with the apparent activation energy. Okay, so we have something self-consistent between the experiment and the theory. So now, but we can do more. Can we isolate intermediate states and complexes? So if we go to CO only, we should be able to access this dicarbonyl, and that's exactly what we can do with experiment. We can actually isolate that and just stay at this state of this dicarbonyl that doesn't react any further. And if we go to oxygen, we go to a monocarbonyl, that's basically what we see in drifts. If we go under CO oxidation conditions, we should see two of these, or basically a mixture of those, one or the other, depending on the reaction conditions, if we're at high temperature or at low temperature. And that's what we see with XAFs, we only see this one. But I have to mention, differentiating between those and XAFs and in drifts, actually from the calculations of the vibration frequencies, they're within 2 wave numbers or 3 wave numbers. We won't be able to see that from infrared spectroscopy. And from XAFs, that's a very difficult thing to differentiate as well. But one thing differentiates these two complexes is their oxidation state. So from DFT, this oxidation state here is on the order of 2.26, and this is through interpolations between the Bader charges with standards of iridium, and the oxidation state of this complex is on the order of close to 3, and this one is 3.3. Okay, so now we go to X-ray absorption spectroscopy again, and from Zane's measurements, the electron deficiency is related to the white line intensity here and also the area under this curve. So we can estimate based on measured known oxidation state complexes of iridium, we can actually get the area under this curve and estimate what the oxidation state is. And that's what we did, and you see actually very surprising agreement between the DFT calculated charges and what we get from the experiment. So the last thing I want to show you, so we were able to isolate these different states. The last thing I want to show you is, based on this mechanism, what you see here, there is a CO on each state, on each one of those complexes throughout the reaction cycle. Is this the same CO, or the CO is actually changing? So is this CO reactive at any of those states, or does it exchange with the gas phase CO, or it doesn't? So that's the question we're asking here. So how do we answer this experimentally first? Is we start with carbon-12 CO. We're reacting in CO and oxygen, and then we switch to carbon-13 CO plus oxygen. If this CO is reactive, or if it's exchanging with the gas phase CO, this peak should shift lower at about here. So we do this experiment, and we do it for over 100 turnover numbers, and we see almost no exchange, very low exchange. If this was exchanging, you would have already seen everything went to carbon-13 CO. So hopefully this convinces you that CO is actually a ligand that doesn't almost exchange at all during this reaction cycle. And through DFT calculations, any of the states that will allow for exchange or will allow for a reaction of the new CO with the existing interfacial oxygen have barriers that are at least 0.6 eV higher than the main cycle that we have. So we don't expect it to be a very fast exchange. And that's what we see experimentally. All right, so to summarize, and actually before I summarize, there is one step that I didn't show here. This existence of this oxygen is actually what stops this exchange. If we only go in carbon-13 without oxygen, you will get exchange, and you'll start seeing all dicarbonyls of carbon-13. So I hope I was able to show you that we can isolate states and identify rate determining steps in a catalytic cycle, similar to what you would do in a homogeneous type catalyst. I hope I was able to convince you that CO actually acts as a ligand throughout this whole cycle. And we also determined how the exchange is inhibited, and I didn't really show these results here, but if you remove the CO, then you start getting exchange. And I want to acknowledge Coogan, who did basically all the experimental work, Lieping and Hongliang for the DFT calculations. All this XAPS work was done actually at NSLS2 with Ellie and Dennis. And the HERFT measurements were done at SRL. Adam, I see him in the audience, and with Simon. And Ray did the microscopy work at OR. And obviously without the funding from here, it would have been possible. And thank you for your attention.
Thank you very much for a nice talk. Any questions?
Homogeneous catalysis type question, but because the CO that you put on there stays on, have you ever thought about putting something else there?
We're working on that. You're absolutely right.
Get better catalytic.
Exactly. That's what we're looking at. That we're also trying to look at the difference in activity between these. Since they're so stable, the dicarbonyl versus the monocarbonyl, and see if we can actually turn over something else on it. You're absolutely right. And we can put an NO or a cyanide, like you said, but we haven't got to that point yet. Yep.
So the resting state was a monocarbonyl?
Yeah.
And you kind of showed...
Well, yes, but a different monocarbonyl can be. Yeah.
And you kind of showed both the absorption and reaction of the CO, the second CO, in a single step. But if your resting state is a monocarbonyl, it implies that the absorption is the hard step. So can you parse that? Can you parse the effect of absorption?
Just from DFT, the issue is this step is basically almost has no barrier. So once it absorbs, so the step that is limiting is the absorption. The next one almost has nothing in terms of barrier. So it's just you limit it by putting it there. So you can think about it as an absorption step or as just an Elie-Redeal type step. So it's not detectable. So you can detect the second CO that is in this state. This state is not stable. It just goes to that state with no barrier.
Any other questions? I have a quick question.
Yep.
It's iridium on a manganese spinel.
So this is on titanium. The first part was on magnesium aluminum.
Do you see big effects based on the support?
Biggest what?
Matrix effects with the support changes?
So surprisingly, we thought when we started this that the reducibility of titanium would make this a better catalyst. And actually it's much lower in activity. And we believe that we're trying to look into what is the reducibility of that complex now that you make on the support. So when you start making this oxygen come out easier, now putting it back actually becomes more difficult. So that's why you're starting to have two rate determining step instead of one on the magnesium aluminum.
Thanks.
Sure.
All right, let's thank our speaker for a very nice lecture.